Imagine you're planning a trip. The first question is, which country are you going to? Once you've chosen the country, you select a city. Inside that city, you choose a specific neighborhood. And finally, you choose the exact house where you'll stay. Finding an electron inside an atom works in a very similar way. Scientists don't describe an electron using a street address. Instead, they use a set of numbers called quantum numbers. These quantum numbers act like an electron's complete address inside an atom. They tell us where the electron is most likely to be found and describe its unique position and properties. There are 4 quantum numbers, and each one provides a different piece of information. The principal quantum number is like the country. It identifies the electron's main energy level. The Azimuthal quantum number is like the city. It identifies the subshell, S, P, D, or F. The magnetic quantum number is like the neighborhood. It identifies a specific orbital within a subshell. And the spin quantum number is like the house. It identifies the electron's spin direction. Together, these 4 quantum numbers give every electron a unique address inside an atom. So let's begin with the first quantum number, the principal quantum number. The principal quantum number, written as n, tells us 2 important things about an electron. First, it tells us which main energy level, or shell, the electron is in. Second, it tells us how big that shell is. Now here's something you need to know. The value of n can never be 0. It can only be 1, 2, 3, 4, and so on. Think back to our travel example. You can't travel to country 0 because it doesn't exist. In the same way, an electron can't be in energy level 0. The first possible energy level is n equals 1. Now here's the cool part. As the value of n gets bigger, the electron is, on average, farther from the nucleus. It has more energy. The shell gets larger, and that larger shell can hold more electrons. For example, if n equals 1, the electron is in the first energy level, closest to the nucleus. If n equals 2, it's in the second energy level. If n equals 3, it's in the third energy level. And the pattern continues. So whenever you see the principal quantum number, n, remember this. It tells you which main shell the electron is in and how large that shell is. Once you get that idea, understanding the other quantum numbers becomes much easier. But hold on, the electron's address still isn't complete. We know the main shell, but not the subshell. So let's uncover the next piece of the puzzle, the Azimuthal quantum number. The Azimuthal quantum number represents the subshells inside a shell. So far, we've learned that an electron has different shells, and those shells are represented by the principal quantum number. Now, inside every shell, there are subshells. Those subshells are represented by the Azimuthal quantum number. Think of it like this. A country has cities inside it. In the same way, a shell has subshells inside it. Now you might be wondering, how many subshells are there in one shell? Well, here's the rule. Number of subshells in a shell equals shell number. So if we're talking about the first shell, also called the K shell, it has 1 subshell. The second shell, or L shell, has 2 subshells. The third shell has 3 subshells. And the fourth shell has 4 subshells. So basically, first shell, 1 subshell. Second shell, 2 subshells. Third shell, 3 subshells. Fourth shell, 4 subshells. Simple enough, right? Now obviously these subshells need names too. The K shell has only 1 subshell, and it's called the S subshell. The L shell has 2 subshells. One is called the S subshell, and the other is called the P subshell. The third shell has 3 subshells. They're called the S subshell, the P subshell, and the D subshell. And the fourth shell has 4 subshells. By now you can probably guess the first 3. The S subshell, the P subshell, and the D subshell, and the last one is the F subshell. Now let me explain all of this using the diagram on your screen. Trust me, this is going to make everything crystal clear. This is the nucleus. Around the nucleus, this is the first shell. This is the second shell. This is the third shell. And this is the fourth shell. Inside the first shell, there's only 1 subshell called the S subshell. Inside the second shell, there are 2 subshells, the S subshell and the P subshell. Inside the third shell, there are 3 subshells: the S subshell, the P subshell, and the D subshell. And inside the fourth shell, there are 4 subshells: the S subshell, the P subshell, the D subshell, and the F subshell. So as you can see, every shell has the same number of subshells as its shell number. Now, take a closer look. There are 4 different S subshells shown here. To avoid getting confused, we give each one a different name. So instead of just saying S, we call them 1S, 2S, 3S, and 4S. Similarly, this one is called 2P. There is no such thing as 1P. The P subshell starts from the second shell, so the naming begins with 2P. Then we have 3P and 4P. The same idea applies to the D subshell. There's no 1D or 2D. The D subshell starts from the third shell, so we have 3D and 4D. And finally, the F subshell starts from the fourth shell, so we have 4F. Pretty neat, right? The Azimuthal quantum number is represented by a small letter L. The value of L starts from 0 and goes up to 1 less than the principal quantum number. For example, if n equals 1, then L equals 0. If n equals 2, then the maximum value of L is 1. That means L can be 0 or 1. If n equals 3, then the maximum value of L is 2. That means L can be 0, 1, or 2. If n equals 4, then the maximum value of L is 3. That means L can be 0, 1, 2, or 3. So the rule is this: the value of L ranges from 0 to n minus 1. In simple words, L starts from 0 and goes up to n minus 1, both values included. That's the rule for the Azimuthal quantum number. One more thing. Instead of remembering the values of the Azimuthal quantum number separately, you can simply remember this: S equals 0, P equals 1, D equals 2, F equals 3. We'll solve questions based on this at the end, so don't worry about memorizing it right now. So let's do a quick recap of what we've learned so far. We learned that shells contain subshells. Now it's time to go one level deeper. Inside every subshell there are orbitals, and those orbitals are represented by the magnetic quantum number. Let's understand that next. The magnetic quantum number represents the orbitals present inside a subshell. So far, we've learned which subshells are present inside a shell using the Azimuthal quantum number. Now, we'll learn which orbitals are present inside those subshells using the magnetic quantum number. The S subshell has 1 orbital. The P subshell has 3 orbitals. The D subshell has 5 orbitals. And the F subshell has 7 orbitals. Simple enough, right? Now, we represent orbitals using boxes. Since the S subshell has 1 orbital, we draw 1 box. The P subshell has 3 orbitals, so we draw 3 boxes. The D subshell has 5 orbitals, so we draw 5 boxes. And the F subshell has 7 orbitals, so we draw 7 boxes. Now here's the interesting part. The magnetic quantum number is represented by m sub L. The number of orbitals is given by the formula: 2L plus 1. Here, L is the Azimuthal quantum number. Let's use this formula. For the S subshell, the value of L is 0. So 2 times 0 plus 1 equals 1. That means the S subshell has 1 orbital. Now let's do the same for the P subshell. The value of L is 1. So 2 times 1 plus 1 equals 3. That means the P subshell has 3 orbitals. Next, the D subshell. The value of L sus is 2. So 2 times 2 plus 1 equals 5. That means the D subshell has 5 orbitals. And finally, the F subshell. The value of L is 3. So 2 times 3 plus 1 equals 7. That means the F subshell has 7 orbitals. So, using the value of the Azimuthal quantum number, we found the number of orbitals in each subshell. Now, let's find the possible values of the magnetic quantum number for each subshell. For the S subshell, L equals 0. So the only possible value is 0. For the P subshell, L equals 1. So the possible values are 0 plus 1 minus 1. For the D subshell, L equals 2. So the possible values are 0 plus 1 plus 2 minus 1 minus 2. For the F subshell, L equals 3. So the possible values are 0, plus 1, plus 2, plus 3, minus 1, minus 2, minus 3. Pretty cool, right? So far we've learned that an atom has a nucleus. Around the nucleus are shells. Inside those shells are subshells, and inside those subshells are orbitals. We've also learned their names, their numbers, and their values. Now, let's go one level deeper. Every orbital can hold 2 electrons. One electron has spin up, and the other has spin down. These electron spins are represented by our final quantum number, the spin quantum number. Let's understand that next. The spin quantum number represents the spin of an electron in an orbital. It is denoted by m sub s. The spin quantum number can have only 2 possible values, plus 1/2 and minus 1/2. Now, what do these 2 values mean? Every orbital can hold a maximum of 2 electrons. One electron has spin up, which we represent with an upward arrow. The other electron has spin down, which we represent with a downward arrow. That's why, whenever you see a completely filled orbital, you'll always see one upward arrow and one downward arrow. Simple enough, right? Now we've completed all 4 quantum numbers. We learned that the principal quantum number represents the shell. The azimuthal quantum number represents the subshell. The magnetic quantum number represents the orbital. And finally, the spin quantum number represents the spin of an electron. That's all the theory you need. Now let's solve some questions and see how all 4 quantum numbers work together. An electron is present in the 3p subshell. Find its principal quantum number, azimuthal quantum number, number of orbitals, and the possible values of the magnetic quantum number. Let's solve it step by step. The electron is present in the 3p subshell. The number before the letter represents the principal quantum number, so n equals 3. Next, we need to find the azimuthal quantum number. The electron is in the p subshell, and we already know that the value of p is 1, so L equals 1. Now, let's find the number of orbitals. We use the formula. Number of orbitals equals 2L plus 1. Substitute the value of L. 2 times 1 plus 1 equals 3. So the 3p subshell has 3 orbitals. Finally, let's find the possible values of the magnetic quantum number. For a p subshell, the value of L is 1. So the possible values of m sub L are 0, plus 1, and minus 1. So our final answers are principal quantum number equals 3. Azimuthal quantum number equals 1. Number of orbitals equals 3. Possible values of m sub L are minus 1, 0, and plus 1. How many electrons can fit in the orbital for which n equals 3 and L equals 1? Options: A, 2, B, 6, C, 10, D, 14. We are given n equals 3 and L equals 1. The value of L equals 1 means the electron is in the p subshell. Now, the p subshell has 3 orbitals, and we already know that each orbital can hold a maximum of 2 electrons. So, total electrons equals number of orbitals times 2 equals 3 times 2 equals 6. So, the correct answer is option B, 6 electrons. All right, here's the next question. The principal quantum number is n equals 4. Answer the following. How many subshells are present? Name all the subshells. Which subshell has the maximum number of orbitals? We are given that the principal quantum number, n equals 4. We already know that the number of subshells is equal to the shell number, so number of subshells equals 4. Now, let's name those subshells. The 4 subshells are S, P, D, and F. Finally, let's find which subshell has the maximum number of orbitals. We know that S has 1 orbital, P has 3 orbitals, D has 5 orbitals, F has 7 orbitals. So the F subshell has the maximum number of orbitals. Therefore, our final answers are number of subshells equals 4. Subshells equals S, P, D, and F. Subshell with the maximum number of orbitals equals F. Now let's tackle another question. An orbital contains 2 electrons. What are the possible values of the spin quantum number, m sub s, for these two electrons? Solution. We already know that every orbital can hold a maximum of 2 electrons. According to the spin quantum number, one electron has spin up and the other has spin down. The value of spin up is plus 1/2, and the value of spin down is minus 1/2. Therefore, the possible values of the spin quantum number for the two electrons are plus 1/2 and minus 1/2. So the correct answer is m sub s equals plus 1/2 and minus 1/2. So with that, we've completed all 4 quantum numbers. Before we end this video, there's one more thing I'd like to tell you about the subshells. Every subshell has its own unique shape, which tells us about the orientation of the electron cloud in space. The S subshell has a spherical shape. The P subshell has a dumbbell shape. The D subshell has a cloverleaf shape. And the F subshell has a much more complex shape. Now let's talk about how many electrons each subshell can hold. The S subshell can hold a maximum of 2 electrons. The P subshell can hold a maximum of 6 electrons. The D subshell can hold a maximum of 10 electrons, and the F subshell can hold a maximum of 14 electrons. These values are very important because we use them while learning electronic configuration. If you want to learn electronic configuration in a simple and easy way, you can watch my dedicated video. In that video, I've explained the complete concept and solved electronic configurations from atomic number 1 all the way to 30. That's it for this video. Thanks for watching, and I'll see you in the next one.